Hello dear students, welcome you all for transmission and distribution class. In the previous class, we have seen the performance of transmission line. In that, we started with the short transmission line, where we are seeing how a short transmission line is modeled with one resistance and inductance and load is connected, neglecting the capacitance, how sending end voltage and receiving end voltage is having the relationship. Now, we will see this solution in the complex notation. Here, in the complex notation, if you it is often too convenient and profitable to make the line calculations in the complex notations. Taking the VR vector, that is the obviously our voltage and currents are in the both has got magnitude as well as angle, so we can use it in complex form only. VR vector as a reference phase. Draw the phase diagram in 10 point. This figure you can see we are taken here VR as the reference. In previously we are taken I as the reference. Now VR as the reference we are taken, and it is clear that Vs is the phasor sum of VR and Iz vectors. Okay. Now, what is VR? If you consider it as a reference, VR vector is equal to VR plus J0 because initially angles are taken considered as 0 as a reference. And I, obviously, we are knowing that I is lagging the voltage. I is lagging the voltage. Obviously, I is equal to I angle minus phi r. Or we can write that one as I into angle phi r is nothing but I into cos phi r minus j sin phi r. We are knowing this one. Any complex value a angle theta is nothing but a into cos theta minus j sin theta. Is it in the same form? And z is nothing but what r plus j xl complex impedance. Now Vs is what Vr vector plus Iz vector, or we are writing this Vr plus J0 into I into cos phi r minus j sin phi r into r plus jxl. After multiplying this one, we will get Vr plus Ir cos phi r plus Ixl sin phi r plus complex terms, that is the j terms are Ixl cos phi r minus Ir sin phi r. Or finding the Vs, total square root of this one, we will get like this, or Vs is equal to, approximately we can write it as Vr plus Ir cos phi r plus Ixl sin phi r. So the following points to be noted are: the approximate formula Vs is equal to Vr plus Ir cos phi r plus Ixl sin phi r gives fairly correct result for lagging power factor. However, appreciable error is caused for leading power factor. Therefore, approximate expressions Vs used for the lagging power factor only. So it is better to go with the lagging power factor only. In leading power factor, it may give some errors. And the solution is in complex notation is more presentable form. Usually it is very presentable form is very easy. Now, three-phase short transmission line, same as the single phase. Instead of single phase, we are using here three phases. Each three phase has got its own resistance and inductances. So you can see in the figure here 10.4 how three-phase load is connected with the three-phase system. As a matter of convenience, a generally analysis of three-phase system is considering one phases only. Therefore, expression for regulation, efficiency, etc. divide for a single phase and also applied for the three-phase system. Since the only one phase is considered, the phase value of three-phase system should be taken. Thus, Vs and Vr in the phase voltages only, and whereas R and XL are resistance and inductance per phase values only. So now here one star connected system is shown. Each conductor has a resistance of R ohms and XL inductance, inductive reactance, and the second figure shows the separate phase, single phase model of the three phase system. So how the single phase and three phase uh, systems are differ, you are seen. Let us see one problem. After that we will see the effect on the power factor and regulation. We will see one problem first. Okay. Yes, have a problem. A single phase overhead transmission line delivers 1100 kilowatt at 33 kV at 0.8 power factor lagging. The total resistance and inductance, inductive reactance of the line is 10 ohms and 15 ohms respectively. Calculate number one sending end voltage, second one sending end power factor and transmission efficiency. So first given data to be write down. First one is receiving end power is PR is equal to 1100 kilowatt Receiving end voltage VR is given by 33 kV. Receiving end power factor is anyhow it is a single phase, no need to multiply or divide it by root 3 anything, directly we can write down. Receiving end power factor is cos phi r is equal to 0.8 lagging. Resistance R is 10 ohms, inductive reactance is 15 ohms. So we need to find what is Vs, what is cos phi s, what is efficiency, and what is the line current. Fine, with the same one complex notation we have to go. Vr vector is equal to what? Vr plus J0, that is 33,000 plus J0. PR we are knowing that Vr IR cos phi r, or we can write here send short transmission lines, we are knowing that sending end current is same as the receiving end current. Instead of IR IS, we can write directly it as I. IS is equal to IR is equal to I only. So PR I can write it as VR I cos phi r. Or if I want to find out the I, PR by VR cos phi r. We know 1100 kilowatt divided by 33 kV into 0.8. I am going to get here current as 41.67 amps. So once I got the 41.67 amps as the current, I need to get the actual current or complex form. So here cos phi r is given, that the value of cos phi r is 0.8. So I can get the value of phi r here. It is a cos inverse of the 0.8. I want the I vector is nothing but I cos phi r minus j sin phi r. So anyhow cos phi r is 0.8 means obviously sin phi r is 0.6, we are knowing. By putting those values here, I can get the vector form of I is equal to 41.664 at angle minus 36.87 as the current, because lagging current is lagging to the voltage, that's why I have taken the angle as negative here. Now the thing is what, Vs is equal to Vr vector plus Iz vector. Z is equal to R plus JXL, that is 10 plus J15, and Vs is equal to Vr plus Iz. So if you write like this, or by putting all the values, I am getting here Vs as 33709 at angle 0.425 degrees. So magnitude of the voltage is given by 33709 volts. So here by writing the phasor diagram, VR IR, if you write the sign phi s is what, the current angle between current and the sending end voltage. So it is nothing but phi s plus phi r, phi s is equal to phi r plus alpha. Alpha is the angle between VR and Vs. So whatever the angle we got now 0.425 is nothing but alpha, because we are taken VR as the reference. Alpha is the angle between Vs and VR. So if to get the phi s, we need to add phi r plus alpha. Phi r is 36.86 and phi s alpha is 0.425. Totally phi s is nothing but 37.286 degrees. So now we got the sending end power factor as cos of this one, that is 0.7956 at the sending end power factor. And finally transmission efficiency, power received by power sent into 100. So power sent is nothing but power received plus losses. Total losses can be given by I square R. So it is 17.358 kilowatt, and power sent is 11 kilowatt, 1100 kilowatt into 17.358 kilowatt. Total it is 17.358 kilowatt, or total transmission efficiency can be got it as 98.44%. So I think this is problem is very easy. You understood this concept. Once again you can go through this problem. See, starting from here, the things are given, data you write down and convert the VR in complex form, that is VR plus J0, and find out the PR is given. Using that equation you find the I. Once you find the I is in complex form, that is I into cos phi r minus j sin phi r. Once you know the I, you can go to find the Vs, that is Vs is equal to Vr plus Iz. So after finding the Vs, you will get the angle alpha. You need to find the phi s angle between I and Vs. Add phi r plus alpha. You get phi s, means that is your Vs angle phi s. Once you find the Vs, you go to find the losses. Once you know the losses, you can get calculate the sending end power, and the efficiency is receiving end power divided by sending end power. You will get the efficiency. Okay, you try the problem by your own. If you find any difficulties, you can ask me. Okay, so in the next class we will see the effect of the some transmission efficiency and regulation. Then we will move to the medium transmission line. Thank you.